Welcome, everyone. My name is Dawn Mullally, and I am the Communications Manager for UCAR.CPAESS. And this position affords me the pleasure of working with our many wonderful scientists, like our guest speaker today. I am delighted to have you attend the CPAS Discovery Seminar Series. CPAS scientists do everything from explore our ocean depths to fly into hurricanes to heliophysicists modeling coronal mass ejections and those who unravel the mysteries of the Arctic. And we want to share all of this with the public, the NCAR, UCAR community, and our many colleagues at universities and agencies across the globe. Just to orient you, we are using Slido so that you can post questions to our speaker, and you'll be able to find access in the tab on the top left of the screen. Today, it is my sincere pleasure to introduce to you our speaker, Dr. Yaowei Li, who is a UCAR.CPAESS scientist researching as a NOAA Climate and Global Change Postdoctoral Fellow, co-hosted at MIT and Caltech. And his research examines how atmospheric aerosols affect air quality and climate, with a focus on wildfire and volcanic emissions. He has developed and deployed instruments on aircraft, drones, ground stations, and in laboratory settings to measure aerosols and gas pollutants from the surface to the stratosphere, integrating these measurements with models to study urban air pollution and aerosol climate interactions. His ongoing work combines satellite remote sensing and atmospheric modeling to study the long-term effects of wildfire aerosols in the global atmosphere. Today, Yaowei Li will share his research with this seminar, From Regional to Global, the Far-Reaching Impacts of Wildfire on the Atmosphere and Climate. Please join me in welcoming Yaowei.
All right. Thank you, Dawn. Thank you so much, Dawn, for this nice introduction. It's my great pleasure today to speak on the CPAS Discovery Seminar. As Dawn mentioned, today I will be talking about some of my recent work in terms of these far-reaching impacts of wildfires on the atmosphere and climate. And I'm going to cover two topics, which ranging from the regional scales to the global scales. So at the beginning, I also wanted to thank all of my collaborators and mentors in the past few years that has been really contribute to the works I will be presenting. So as we all know that wildfires is really a burning issue, especially as we are facing a warming climate. So here I'm just showing you a few examples in the past few years that has been those record-breaking wildfires has been happening all over the world, including like last year, the very horrible like urban and wildland interface wildfire in Los Angeles, as well as the 2023 the Canadian wildfires, and also like in the 2019-2020 Australia wildfires. All these fires has been happening. And they have been getting more and more severe and frequent with the warming climate. And a very important fact about wildfires is that what burns locally doesn't stay local. So we have wildfire happen in the source to regional to local regime, but the smoke that emitted from those wildfire burnings can be transported in the atmosphere to the regional and even to the global regime. That's the reason that why we want to study these long-lasting and far-reaching impacts of wildfire and how they affect the atmosphere and the climate. So the reason that this smoke can be transported to further distance is because actually the atmosphere has different kind of the structures or the layers. So this is actually one of my favorite photos that we took in one of the field campaign I participate in. So we were using two of the NASA aircraft. So on the center, you can see this high altitude WB-57 airplane. And then on the bottom right here, you can see another high altitude plane called ER-2. So during that mission, we put a GoPro camera on board the ER-2 airplane, and it actually, while it's flying in the stratosphere, it took this very nice photo, shows like clearly the distinction between two of the most important layers of the atmosphere, which is on the bottom is the troposphere, which ranging from the ground to about 6 to 17 kilometers, depending on the latitude. It can vary a lot in terms of the top of the troposphere. And above the troposphere is another layer we call the stratosphere, which is from the top of the troposphere to about 50 kilometers. And these two layers have very different kind of characteristic. So in the troposphere, the particles or the smoke or other different species have relatively shorter lifetime because it's highly turbulent. So when you have the smoke emitted, especially in the lower troposphere, it typically get cleaned away in about 7 to 10 days time scales. But if the smoke can be transported higher up into the upper troposphere or even into the stratosphere, the smoke can stay much longer lifetime because in those layers, the air mass is much more stable. So for example, in the stratosphere, the air mass or the smoke can stay in the atmosphere for several months or even 2 years. So depending on at what altitude the smoke get injected to, they can actually get transported away, like that is far from the source of the fire and can stay in the atmosphere for much longer time and impose much longer impacts to the atmosphere and to the climate. So, and these kind of the far-reaching impacts is really affects our daily life. So wildfires are reversing decades of the air quality improvements across the U.S. So on the bottom up here, on the top left here is a photo that I took from the New York Times report that showing during the 2023 Canadian wildfire season, the smoke gets transported all the way down to the east U.S. And you can see that Canadian wildfire actually caused the very severe air pollution in New York City. And within this wildfire smoke, a very important pollutant, and also that cause very bad visibility, is something we call particulate matter, especially something we call PM 2.5, which is the particulate matter or the particles that is smaller than 2.5 microns. So each single particle is very, very small. It's only about tenths of the thickness of the human hair. But if you have a large amount of these tiny particles in the air, it can actually cause very significant impacts on the visibility as well as on the public health. There are studies that published a few years ago showing that the PM 2.5 shows steady declines through 2016, and then the stagnation or reversal. So as you can see on for the average on the whole continental US, we can see a steady decline starting from early 2000 until around 2016. And we see this sort of like stagnation or the reversal trend of the annual average of the PM 2.5 concentration. And this study actually attribute this stagnation or the reversal to the wildfire smoke. If we also actually look at this trend in the west part of the US, we can see the reversal trend is becoming more significant, mostly because there are actually more frequent and severe wildfire happens on the western part of the US. So the wildfires are really reversing these decades of the air quality improvement across the US. And another big reason for us to study the wildfire smoke or the aerosol particles within the wildfire smoke is that these aerosols actually play a very essential role in moderating the Earth's energy balance. So some people might heard of a term called radiative forcing, which basically means that these aerosols can change the Earth's energy balance by either like we call it direct impacts, which means the aerosol will directly scatter or absorb incoming solar radiation, or it can have some so-called indirect impacts, which means these aerosols can modify a cloud in the atmosphere. And by changing either the cloud properties or cloud lifetimes, it can further change how cloud interact with solar radiation and affect the Earth's energy balance. And actually, based on the most recent IPCC report, we know that aerosol cloud and aerosol radiation impacts actually represent the largest source of uncertainties in our current understanding of climate change and to prediction of the future climate change. So this is actually a very big motivation for us to better understand the aerosol properties and how wildfires may contribute or modify the aerosols in the atmosphere and then further change the climate. So today, in my talk, I will be talking two parts of the story. The first part will be focusing on the unexpected regional radiative impacts from a very interesting phenomenon called wildfire-driven thunderstorms. And in this part, I will be combining the instrumentation, airborne measurement, as well as the modeling together to probe this question. And then I will transition to the global impacts. I'll be talking about some of the global temperature responses to the major wildfires and compare those impacts with the significant volcanic eruptions. And I will be using both modeling data as well as the satellite remote sensing. So the first part will be focusing on this regional scale and look at the regional radiative impacts from this so-called wildfire-driven thunderstorm. And to begin with that, I want to give a quick introduction about what is wildfire-driven thunderstorm. So this has actually been, in the past few years, has becoming a very, I would say, like popular word that has been showing up in the different news. So basically, the concept is in the favorable meteorological conditions, when you have these very big wildfires, the wildfire could emit a huge amount of heat and moisture, and that could potentially develop its own thunderstorm that react as a chimney to rapidly transport the wildfire smoke to high altitudes, and it can be several to tens of kilometers and further to the distant region and even globally. And we call this phenomenon pyrocumulonimbus, or the short name of pyro-CB. The pyro-CB has been known for like more than 2 decades, but the climate impacts of these pyro-CB or the pyro-CB aerosols remain highly uncertain, mostly because we have very, very limited direct measurement of this high altitude pyro-CB smoke, as we can imagine, because the smoke can be transported to several to tens of kilometers above the ground. So there's just very few platforms can reach to that high altitude to do the direct measurement of the properties within that smoke. So luckily, during one of the aircraft mission that is funded by NASA, we had an opportunity to actually probe the different properties within that pyro-CB smoke at high altitude. So this is a mission that I participate in. It's called Dynamics and Chemistry of the Summer Stratosphere, or the short name of DCAS. And this mission is dedicated to observe the stratospheric outflow from the overshooting thunderstorms. And the mission ended last year, and it was started on 2019. So as you can see, we were using this NASA ER2 high altitude airplane, which can fly up to about 21.5 kilometers. So which really gives us the power to fly into this high altitude smoke and even higher above that to examine the properties within that smoke and provide some of the direct measurements to help us to constrain the different properties of this smoke and how they further affect climate and air quality. I will be focusing on the aerosol part of this mission, so I want to give a little bit introduction about the aerosol payloads of this campaign. So as I mentioned, the mission happened, the deployment happened in 2021 and 2022 during summertime. So on the bottom left here, you can see the flight track during our field campaign. We have total about 31 flights, and you can see the flights has been flying over continental US, all over across the continental US, and we also have a few flights that fly over Canada. There are three different aerosol payloads inside the nose of the airplane. So the first one is a single particle mass spectrometer measurement, which basically provide the chemical composition of each single particles we measured. And then the second instrument is called Mini-Moody, which is a particle sampling system. So we can sample the particles from the stratosphere or from the upper troposphere and bring those particles back to the lab to do more detailed analysis. The third instrument is called a DPOPS, which can do the in situ particle size measurement. So it gives us the real-time size distribution measurements in the within the smoke or in the background conditions. So with the combination of this chemical composition and microphysical measurement, we can have some good understanding about how the smoke might perturb the high altitude environment. And I want to give a little bit more introduction about instrumentation because this is actually a big part of my work during this aircraft mission. So I spent a few years in a lab to sort of develop this instrument so that it can be used and deployed in these high altitude platforms. So on the left, which is a picture showing the nose of the ER2 airplane, and on the center here, you can see the instrument that we built to measure the aerosol size distributions, ranging from about 140 nanometer to about 2.5 microns. And with the careful design of the instrumentation and also the sampling line, we can do so-called isokinetic sampling from the near surface environment up to the stratosphere, so across a very wide dynamic ranges. And as you can see, the instrument is really compact. You can actually put the whole instrument on the suitcase, and you can just do the normal like tracking luggage with the commercial flight. So the reason that being this compact is because we want to design to be really easy to install and disassemble from the airplane, and it also can be easily adapted to a different airplane platform. So every time I talk to my friends or other people about those airplane or aircraft missions, people would ask me about how does it feel like to be on an airplane, especially this very cool NASA airplane. So unfortunately for those high altitude platforms, there will be no scientist or engineer on board the airplane because these airplanes are not pressurized nor temperature controlled. So as you can see on the left of this picture, this is a pilot. The pilot actually need to wear something like a spacesuit to maintain the pressure and temperature. And then there will only be the instruments on board the airplane together with the pilot. But it's still really fun to participate in this mission because as a scientist myself, what we do in the field is that so before each flight, we need to install the instrument on board the airplane, and then after each flight, we need to kind of disassemble the instrument from the airplane and to do like calibration, the data check, everything. So it's really fun to be working on this plane, although we cannot be on board during the flight. Okay, now let's take a look at some of the interesting results we got. So as I said, kind of one of the goals for this flight is to target the so-called young perturbs smoke, which means the smoke has been aged in the atmosphere for only a few days. So the first step for us to measure or to sample the perturbs smoke is to target the smoke to find where the smoke is so that we can guide our airplane to sample them. So we use the different satellite platforms, satellite measurement to guide our flight planning. So this is just a few of the different satellite images. So the first one is that using the geostationary satellite, we can actually pinpoint the source of the wildfires. And we can see in day one, which is around June 2022, we identified a developing pyrocv event. So we can actually pinpoint exactly where the active fire is. And we can actually also, based on some other remote sensing techniques, we can identify the smoke top as well as the injection height of that pyrocv smoke. And then we would just tracking this smoke using the different, for example, the geostationary satellite and some other satellite platforms to track the plume of this smoke. And then on day 5, finally, we got everything ready for our airplane. We got an instrument team and other modeling team ready. So we made a flight plan. We fly the airplane and to intersect that smoke. And we were very successful in terms of sampling this smoke. So what I'm showing you here is the time series. On the x-axis is the time, and the time series of the aerosol size distribution. So on the y-axis on the left is the diameter or the size of the aerosols, and the color here showing the number concentration of the aerosol particles within each diameter beams. And I also overlaid the flight track here, so that you can see the altitude of the flight while we sample the atmosphere. And the altitude can be read on the left part of the y-axis. So as you can see on this figure, the ER-2 airplane was flying up and down in the atmosphere, and when they hit the smoke plume, we suddenly see a dramatic enhancement of aerosol concentration. So you can see all this red color here showing the high concentration of the smoke plume. And these smoke particles are also very large particles. So if you look at the left y-axis, these particles can be as big as 500 to 600 nanometers. And because we were chasing this plume, so we know the smoke plume we sampled were 5-day old, and they are between 14 and 15 kilometers. So now let's zoom into this wildfire smoke and take a deep look at the size distribution and composition within this smoke. So what I'm showing you here is the volume density distribution of the particles within the wildfire smoke, and you can see it shows a very sharp distribution with a peak diameter around 500 to 600 nanometers. And within this smoke, most of the particles are biomass burning particles based on our chemical measurement. And it's more than 85%, which actually really give us the confidence that we sampled wildfire smoke instead of some other features. And when we first saw this picture, we were very surprised about these larger particles. This is surprisingly large because if you compare this particle size distribution with the typical smoke aerosols we sampled in the troposphere or in the lower atmosphere, we know very well about this typical smoke aerosol size they ranging from 200 to 300 nanometers. But for this high altitude pyrocv aerosols, they ranging from 500 to 600 nanometer diameters. So the question came that why does this particle become so large? So in terms to answer these questions, we actually turn to a simple box model or microphysical model to simulate the growth of these particles under different conditions. So one of the hypotheses is that we have very efficient particle coagulation process at this high altitude. So the coagulation basically means if you have a bunch of small particles, when they hit with each other, they will stick with each other and then stay as a whole and to grow particle to a larger size. So we simulate this aerosol coagulation process in our models. As you can see, we start with a large amount of small particles. The particle size is around 100 to 200 nanometers. And under these stratospheric conditions, because it's very stable in the stratosphere or in the upper troposphere, so the air mass can actually stay together as a high concentration for a relatively longer time compared with the lower atmosphere, which just favors the coagulation process in that high altitude. So what our model shows is that only after a day or two, these small particles can very efficiently grow from this small size to the larger size, and then stay around these 500 to 600 nanometer for relatively longer time, which is consistent with what we measured in the field. So this really provide us some of the convincing evidence that this efficient coagulation can explain the larger size we measured for these high altitude smoke aerosols. And we think this can be a very universal characteristic for these high altitude smoke aerosols. So people might wondering, okay, so why do we care about this larger size versus the small size? So that's also the questions we ask. Why does it matter? Like, what are the difference these larger particles can make that can be distinctively different from the small particles based on our traditional understanding? So it turns out that these larger particles can cause some very different like climate impacts or radiator impacts. So what I'm showing you here is the calculation of the aerosol radiated forcing at top of the atmosphere. So what I did here, what I'm showing on the x-axis is the diameter of these aerosols, and on the y-axis is the top of atmosphere radiated forcing. So I input the aerosol size distribution we measured based on our field data, and input that into a radiative transform model, and we can calculate the top of atmosphere radiative forcing, which shows us a very significant negative number. Basically means these aerosols at top of atmosphere, they actually cause some of cooling effects of the whole atmosphere. And the more interesting thing actually comes when we compare these larger particles with what typically used in the models. It can be different climate models or the larger scale, like chemical transport models. So I studied a wide range of different model configurations. So typically in different model settings, they represent these wildfire aerosols to be the smaller size. They can be ranging from about 100 nanometer to about 400 nanometers. But most common representation is about 200 to 300 nanometers size. So as we can see, if we compare what we measured with what typically modeled, there's about 35% underestimation of the top of atmosphere radiated forcing, which means the models can significantly underestimate the cooling effects of these larger pyrocb aerosols at top of atmosphere. And the underestimation can be about a third, which is a very big number. We also actually input our measurement into a more realistic models. So here, what I'm showing you is we actually modified a meteorology and chemistry coupled model called WolfGC. So within these models, what I'm showing you here is the difference between the updated and default model simulation in terms of the top of atmosphere shortwave radiated forcing. So by meaning the updated model is we actually replace the smoke aerosols in the models. The default size is small size, but we replace this small size to the 500 nanometer size we measured. And as we can see, by doing this simple update, we can already see the enhanced radiative cooling, which is represented by this blue color across a wide range of the region. So when you have the smoke cover, so which basically shows the consistent result as our radiative transform model, that if you have these larger aerosols caused by these pyrocb smoke aerosols at high atmosphere, these larger aerosols would cause much stronger radiative cooling and can potentially over a broad region than the typical model assume. And also need to see that the wildfire aerosol microphysics remain very poorly represented, especially in a larger scale model. So there's a lot of things we can do and we can improve for these larger scale models for them to better simulate the current climate as well as prediction for the future climate change. And the second part, I'm gonna switch gear a little bit to from this regional scale impacts to the global scale temperature responses. And I will be combining both the satellite remote sensing and the climate model simulations to answer this question. In this part, I will be focusing on a very big event that happened in 2019-2020, which is a so-called Australia Black Summer wildfires. So the wildfires started in around like December 2019, but it continues to like January 2020. So this wildfire event actually injected about 1 million tons of the smoke particles into the lower stratosphere. So what I'm showing you here is another geostationary satellite image showing the southern hemisphere, and you can see this picture shows like only a few days post-fire, you can already see the smoke particles that is surrounding the whole southern hemisphere, which has been shown in this kind of like brown to dark color. So this extreme wildfire can actually significantly disrupt the global atmosphere. And it would be very interesting actually to compare these significant wildfire events with some of the also kind of major volcanic events, because the scientific community has been known for a long time. We have known that for a long time, the major volcanic events can significantly perturb the global atmosphere. So we can see if these wildfire events can actually cause some similar impacts to the global climate that might be comparable to the volcanic events. So in this study, we compare the Australia wildfire events with the classic 1991 Pinatubo eruptions, which injected about 20 million tons of the sulfate aerosols in the atmosphere, and a majority of these aerosols actually made its way into the stratosphere. Another very interesting volcanic event actually happened only a few years ago. It's the 2022 Hunga submarine eruptions. So this volcano is really, really interesting because it's instead of injecting a huge amount of aerosols into the atmosphere, it injected a very large amount of water vapor into the atmosphere. It's about, based on estimates, it's about 150 million tons of water vapor. And we know that water vapor is a very strong greenhouse gases. So it will also be very interesting to look at how these water vapor could cause some of the climate impacts at global scale. And it'd be really interesting to put those three events together because each of them actually impose very different materials into the atmosphere, and they both cause some of the kind of significant impacts onto the atmosphere. Another motivation for us to look at those three events, especially the Australia wildfire and the Hunga eruptions in the recent years, is because that there's a big debating in both the scientific community as well as the general public talking about so-called the acceleration of the global warming. So as we know, like in the past few years, we have been experiencing some of the record-breaking global average warming on the Earth's surface, and people still don't quite understand what causes this record-breaking warming. So that because some of the anthropogenic influence, or that warming mainly come from some of the natural events. So my argument is that in order to understand the climate responses to the anthropogenic climate change, it's really essential for us to understand how the climate responds to some of the natural forces, including the wildfire events or the volcanic events. So to that aspect, it's really helpful for us to actually look at some of the global climate impact from the wildfires and from these extraordinary water vapor injection from 2022 Hunga eruption. So okay, so let's look at the data. So what I'm showing you here is the global mean temperature responses to the wildfire and volcanic perturbations. So this is the time series of the global mean temperature anomalies back to 1986 until the end of 2024. And I'm showing you this time series for three different sort of broad layers of the atmosphere. On the bottom, you can see the average of the troposphere, which is ranging from about 0 to 13 kilometers. And in the middle, which is the so-called lower stratosphere, which is about like 15 to 20 kilometers. And on the top is the mid to upper stratosphere, which is about 35 to 40 kilometers. And this is the observational data from the satellite measurements from this microsounding unit and stratospheric sounding unit. And you might be surprised to see, like, even in the troposphere, we don't see any global warming signals, like the temperature doesn't increase with time, or in the stratosphere, you don't see any of the decreasing of the temperature. This is because I have already processed this data, so I detrended these long-term kind of the greenhouse gases impacts. And I also removed some of the known climate variabilities, including the El Nino events, as well as the solar variabilities. So by removing those known climate variabilities, we can better see the signals from either the wildfires or the volcanic perturbations. So, okay, let's look deep into this time series. So the first thing that actually caught our attention is this 1991 Pinatubo, during the Pinatubo volcanic eruption period. So after the volcanic eruptions, we can see a very significant warming in the stratosphere. That is because the sulfate aerosols get injected into the stratosphere, and those aerosols are very can absorb the long-wave radiation that have been emitted from the Earth's surface. And once it absorbs the radiation, it can warm up the stratosphere. But it's also a very strong, these sulfate aerosols are also very efficient in scatter the incoming sunlight radiation back to the space. So that means you have less energy input into the Earth system. So that's why in the troposphere, it actually cools the Earth's surface, and it actually has been well known. So actually, about 2 years after these Pinatubo eruptions, the global mean temperature decreased about 0.5 degrees. And if we look further down into this time series, we saw another very, very interesting phenomenon, which is around the time of these 2019-2020 Australia wildfires. And we see that these wildfire injections actually causes the largest stratospheric warming in this century or since the Pinatubo period. This is because the wildfire, this 2019-2020 Australia wildfire injected about 1 million tons of the smoke aerosols into the lower stratosphere. So even though the total mass of the smoke aerosols is only about 5% of the sulfate aerosols injected by the Pinatubo events, but you can see that the peak warming is almost half of the peak warming that caused by the Pinatubo. This is also because of very distinct optical properties of these aerosols. The smoke aerosols, as we know, they have something we call the black carbon or brown carbon. They are very efficient in absorb solar radiation, so it can dramatically warm up the stratosphere efficiently compared to the sulfate aerosols. So that's why it causes very, very significant warming in the stratosphere, even though the total mass is only 5%. And if we further look down into this time series, we start to notice these 2020 Hunger submarine eruptions, and especially the water vapor impacts. So the water vapor has been mostly injected into the higher altitude, into the middle to upper stratosphere. So we can see that these cooling effects from the water vapor, because the water vapor is a very strong greenhouse gas, and greenhouse gas in the stratosphere actually cools the stratosphere. So we start to see this very significant cooling at higher part of the stratosphere, upper part of the stratosphere. So it's already very interesting to see this only just by qualitatively look at the time series. But we want to be a little bit more quantitative. And the question we want to answer is that whether, when, and for how long this wildfire and volcanic induced signals can be distinguished from the internal climate variabilities. So to answer that question, we use a signal to noise ratio analysis. So basically, what I'm showing you, what I'm using here is so I define a temperature perturbation that is associated with either wildfire or volcanic eruptions as signals. And I define the internal climate variabilities as noise. And if we assume a Gaussian distribution of the noise, and we can have, if we have a signal to noise ratio that is either above 1.96 or below minus 1.96, we can have 5% significance level of these global significant temperature signals. And in order to get this both signal and noise, we need to rely on both observations and as well as the climate models. So the signals can be actually directly estimated from satellite observations. So which is what I'm showing you here. We can use these global mean temperature anomalies to directly estimate the signals based on the anomaly, measurement anomaly. And in terms of the noise, we actually use 3 different ways to estimate noise because we want to be very robust in our noise estimation. So we take both the modeling method. So we use the kind of the large ensemble of climate models taken from the CMIP6, and we use the both pre-industry control runs as well as historical runs to estimate the noise. We also use the satellite observations itself to estimate noise. And this is because we want to be a little bit more conservative in our statistical interpretation. And let me show you an example of the signal compared with the noise. So what I'm showing you here is if we take a 4-month average period, and if we focus on these Australia wildfire signals and also the noise distributions in the lower stratosphere. So as you can see, like these 3 different colored bars are showing the noise distributions based on 3 different method estimations, and they actually agree with each other broadly. And it shows kind of the noise distribution centered around 0, which makes sense. But if we look at the signals, which has been shown in this kind of vertical red line here, the signals is way beyond the noise distributions. And if we calculate signal to noise ratio, it's a very high values, about like 7.2, which is way above 1.96 thresholds we defined, which means that there's basically impossible for the kind of internal variability to explain that signal, this larger signal. So we can be very confident that this signal is detectable in the global scales and is caused by this wildfire event from the 2019-2020 Australia wildfires. So by using this method, we can actually, there's no reason we only look at one, like 4 months mean, or only look at one layer. We can actually look at this event or 3 different events as a function of time. So what I'm showing you on the x-axis is the averaging window length. Basically, what I'm showing you just now was just 4 months, but we can look at it from like ranging from 1 month to even like 3 years. And on the y-axis here is the signal to noise ratios. And now these 3 different colors here represent 3 different events, including the Pinatubo, Australia wildfire, as well as the Hunga submarine eruption. So now let's first look at the lower stratosphere. So it's not surprising that we can see a very significant Pinatubo signals as being well studied. But what really surprised us is about these Australia wildfire events. So you can see this event is represented by this red color, and the Australia wildfire events can be significant for almost 8 to 12 months after that fire injections. And this is again, I want to highlight this is a global mean scale. So that means that single events cause some of global mean perturbations. And this is globally statistically detectable in the lower stratosphere. And we can also look at it higher up, look at this mid to upper stratosphere, which showing 3 different events. But now we start to see these very, very significant signals from the Hunga submarine eruptions, mostly from the water vapor radiative forcing, because the water vapor, again, in the stratosphere, it cools down the stratosphere. That's why we see the negative signal to noise ratio. And this significance or the detectability can last for almost 3 years. People might also care about how does this event affect the troposphere. So we do look at that as well. So in the troposphere, we start to see the significance of the pinot which is again agrees with our classic understanding. But we don't see any of the robust signals from either Australia wildfires or from the Hanga submarine eruptions in the troposphere, which sort of tells us that is sort of not statistically significant for those natural events to significantly affect the global tropospheric temperature signal. So, which going back to this big picture of the past few years of this very record-breaking warming, so that might point to some other phenomena and actually may point stronger to some of the anthropogenic influence to the climate in the past few years. Okay, so that's the second part of my talk. So I just wanted to quickly summarize here of what we learned so far. So we know in the source to local region that especially with the warming climate, wildfires are projected to increase in both frequency and also severity in this source to local region. And the very important fact is that smoke knows no borders. So once the smoke gets emitted into the atmosphere, it can be transported away from the source to the regional, to even to a global region. So my study or the work I just presented actually really highlights some of the importance of these far-reaching impacts of wildfires. So in the regional to global scale, we find that the models can actually substantially underestimate the radiative cooling effects of these so-called pyrocb smoke particles, because these models doesn't represent this larger size of these particles that has been measured by our recent airborne missions. And in a global scale, we find some of the extreme wildfire events, such as the 2019-2020 Australia wildfire, can significantly disrupt the global atmospheric temperatures and cause some of the statistically significant temperature signals in the global mean scale. So, and both part of the studies has been recently published. So if you're interested, I also include the QR code here. You can feel free to scan the QR code and read more details about these two studies. And feel free to reach out if you have any questions. So and I also want to acknowledge the funding support, which actually also include the support from UCAR through these NOAA Climate and Global Change postdoc fellowships, which has been instrumental to help me to support me for the work I just presented, and also including a wonderful group of collaborators that contribute to the work I present. It's really a team effort. So with that, I will just stop here, and I'm happy to answer any questions.
Thank you so much for sharing your work, Yaowei. We truly appreciate it. And you did a great job trying to simplify some very complex ideas, which I personally appreciate very much. Now we will begin our Q&A portion of today's seminar. I'd like to direct everyone's attention to Slido so that you can ask your questions either with the QR code or the tab in the upper left corner of the screen. While you are doing that, I would invite you to check out our webpage, cpaess.ucar.edu, for upcoming seminars. Our next scheduled seminar is in June and will be presented by Dr. Anne-Christine Zinkin, CPAESS Program Specialist at NOAA's Global Ocean Monitoring and Observing Program. Please go to our website for details. And you are also invited to find this talk and all of our past talks, seminar talks, on CPAESS's YouTube channel. Okay, we have our first question from David Fillmore. Have you or do you have plans to compare your TOA smoke radiative effects to satellite SW radiometer measurements, for example, series. Also looking at surface perturbations.
Yes, that's a very good question. Thank you for that. No, yeah, we have been thinking of that. That's a very so I assume you were referring to this slide. So this one is so I would also need to clarify. This is only for like a one assuming we were measuring, we were calculating that for the smoke, the whole column of the like have the smoke coverage. So this is not a global mean number. So, but it would be really interesting to see some of compare that with some of the remote sensing data, especially because we're now experiencing kind of the higher frequency of the piracy bee smoke. So, especially during the summer season or during wildfire season, I would assume it could have some larger scale impacts, even though here I only look at a single event. But if we considering like multiple events together, I would see like probably compare that with some of the remote sensing measurement. It would be very helpful and insightful. Yeah.
So I would invite people to put their questions in, but in the meantime, this is from a non-scientist here. I thought it was really cool how you figured out that the wildfire aerosols were much bigger than anticipated, that they kind of combined and became much larger than you thought. And you mentioned
Yeah.
that that has a cooling effect. Can you can you explain that when it comes to like on the ground, the wildfires happening? What is that cooling effect like? How would we see that or notice that, or how is it impactful?
Yeah, that's a very good question. Especially, I think um, they also it really depends on like at what region are we talking about, or at what altitude are we talking about? Um, so because a lot of people, when we think about wildfires, we know that wildfire can absorb solar radiation. And actually, on the second part of my talk, I talked that in the stratosphere, this wildfire like warm up the stratosphere. So this is actually true that when you look at the layer or the region of the atmosphere that has the wildfire smoke, so it will absorb the solar radiation and warm up the atmosphere. But what I'm showing you here in terms of cooling effects, this is the cooling at the top of the atmosphere, which is basically the balance of the incoming radiation and outgoing radiation. So, and the cooling is actually largely come from the scattering part of these smoke particles, because even though the particles can still absorb a significant amount of the radiation, but it's also very efficient in scatter radiation back to space or the sunlight back to space. So, and the larger the particles is, or I need to be careful, like within these kind of like submicron regime, like a few hundred nanometers regime, the larger the particles you have, the more efficient these particles can scatter sunlight back to space. So that means compared with these small particles, for example, like 100 to 200 nanometer particles, these 5 to 600 nanometer particles are much more efficient in scatter sunlight back to space. So that's why on top of the atmosphere, you would see much more sunlight get reflected back to space. So it basically cools up the whole Earth system. So that's why I was referring to these sort of radiative cooling effects at the top of atmosphere. And that could potentially also hold true if we are talking about observing from the surface, because if you scatter more sunlight back to space, that also means you have less sunlight reaching the surface, right? Because that has already been blocked by the smoke plume at high altitude. So yeah, so that's it's really depending on at what region you are talking about. So you might hear different term of warming or cooling.
Mhm.
Yeah.
Very interesting. Um, oh, we have another question here from Elisa, sorry. Would you expect a change in the observed top of the atmosphere aerosol size depending on fire radiative power? How was the fire you sampled compared to other fires?
That's another very good question. Um, yeah, so that's absolutely the right question because here we only sampled one fire, one smoke, in 1 year. So how can we generalize it to other these piracy B fires? So that's why we actually use these so-called like the microphysical models to kind of trying to explain these hypothesis, which is this efficient coagulation because in our models we actually we just we represent the initial conditions with a kind of very common scenario from this wildfire. Uh, um, Different kind of wildfire injections, they typically give us the starting point of this small particle size, and then we just input the kind of the common environmental conditions in the stratosphere or in the upper troposphere. So this is not specific to the measurement we had. This is a very kind of the typical environmental conditions at that high altitude. And we just let the model runs and we find given a very kind of typical conditions in that part of the atmosphere, we start to see the coagulation plays a role to grow these particles to this larger size, 5 to 6 nanometer part. So based on this, we sort of, I think it's reasonable to think this efficient coagulation actually applies to a wide range of different fires or different particle size, because in this model, we didn't give any information about the specific fire type or specific chemical composition of the smoke. We just give it a typical like starting point, a typical environmental conditions, and we start to see the size, the coagulation play a role. So that's why we would argue is it could be generalized to other different fires. But of course, we need more data. That's why I'm actually also part of a upcoming NASA-funded aircraft mission called Inspire that we're gonna be using this ER2 airplane again, and some of the in situ is actually a G5 plane that is operated by the NSF NCAR. We're gonna be sampling like a wide range of different piracy B events, and hopefully the data from that campaign can give us much more data set to better validate our hypothesis and test our hypothesis and give us much better understanding about these really limited understanding field. Yeah.
Excellent. We have another set of questions. So question one, what optical property assumptions do you use to calculate the stratospheric radiative effect of the larger particles? And question two is how do 2019, 2020 net wildfire smoke emissions compare to other years? And how much came from the Australian fires?
Yeah, so I will answer your first question. That's also a very good question. It's mostly relevant to this slide, I think. So when we calculate the radiative forcing, we need to kind of prescribe different optical properties, or here we use refractive index. So that's, but we don't have any measurement of it. So, and I don't think we have some very good data set in terms of the stratospheric piracy aerosols. So that's why if you see this, we have an error bar here. The error bar here is like we use 5 different refractive index scenarios that actually based on the different either like the ground-based remote sensing measurement or the aircraft measurements of the wildfire smoke. They are not strictly stratospheric wildfire smoke, but they're just wildfire smoke that's been measured in the past missions. And we use 5 different scenarios of that, and we actually prescribe these 5 different scenarios to all consistently to all the different calculations I have, and that's why we have this uncertainty. So and yes, so based on our conclusion is, if you have larger particle size, you get more kind of more negative radiative forcing, and I think that conclusion holds true for no matter what refractive index scenario or optical properties you use. But again, I think the question is exactly right. We need more data to actually narrow down the uncertainties or error bar here. So so far we don't have good data to constrain the optical properties. And the second question, I think, is about talking about the Australia wildfire.
Yeah.
I don't.
Yeah.
Yeah, can you repeat it again?
Betcha. It's how do the 2019-2020 net wildfire smoke emissions compare to other years, and how much came from the Australian fires?
Yeah, that's a good question. I don't I don't have that number on top of my head right now. So yes, so I know like the number reported is like specifically for this Australia wildfire is about 1 million tons of the smoke get injected, and a majority part of it like get it injected into the lower stratosphere. But of course, there will be fires like other places, like in the southern hemisphere as well in that year. So yeah, but I'm sure there are that studies or report on that, but I just don't have that number on top of my head right now. Yeah.
Excellent, excellent. Well, clearly you've stoked a lot of interest here. Um, We are just past the hour, and so I'm going to wrap us up. But I would like to thank everyone for coming to the UCAR-CPAESS Discovery Seminar. And remember, you can visit our website at cpaess.ucar.edu to find out about future talks. And you'll also find a link for this talk and other past talks once it's uploaded to YouTube. Yaowei, our sincere thanks to you for sharing your important research with us. I would also like to thank CPAS staff Alex, along with Calvin of the UCAR Multimedia Services for his invaluable assistance. And I hope to see everyone on our next CPAS Discovery seminar. Have a lovely afternoon, everyone.
Right. Thank you, Dawn, and thanks
Thank you.
everyone.